All right, good morning. Okay, today I'll be continuing on the subject of alcohols, ethers, and thiols. I'm going to share my screen. Okay, when we left off, we were looking at ethers, specifically naming of ethers. And I will, there we go. Okay, ethers will have this structure. They differ from alcohols in that the oxygen is bonded to two carbons rather than to a carbon and a hydrogen. Okay, because of the two lone pairs on the oxygen, ethers have a bent geometry. And so they do have a dipole moment as a result. All right, here are some common examples of ethers, particularly the first two. Okay, we'll first look at naming. Okay, just like with any organic functional group, the parent alkane is the longest carbon chain that contains the principal functional group. We name the OR group as an alkoxy substituent. And for common names, we'll name the groups that are bonded to the oxygen followed by the word ether. Okay, so this first one is ethoxyethane. Okay, our longest chain, no matter which way we look at it, is ethane. And this is an ethoxy group. The common name is diethyl ether. This is sometimes called simply ethyl ether or even just ether. Okay, if you hear the word ether, it usually means this compound right here. All right, this is MTBE, tert-butyl methyl ether, and its IUPAC is 2-methyl-2-methoxy propanol, propane. Okay, this is not correct here. Okay, this third one makes an important point, and that is that as substituents, ethers have a low priority. Okay, so the alcohol takes priority, and it's assumed to be on carbon number 1, and this is an ethoxy group. Okay, so for ethers as substituents, this is methoxy. Ethoxy. Propoxy. If we had an isopropyl group, it would be an isopropoxy. Right, a benzene ring as a substituent is a phenyl. And this as a substituent would be phenoxy. Ethyl ether or diethyl ether is still used as a solvent. It's a very useful solvent. It dissolves lipids very well from plant and animal material, and it has the advantage of being volatile, so you can readily evaporate the ether. At one time, it was used as an inhalation anesthetic. Its use as an anesthetic goes back to 1846 at Massachusetts General Hospital, and it was used for probably about a century as an anesthetic. There were some problems with using ether as an anesthetic. Okay, oftentimes when the patient would awake, they'd be very nauseated, and there were also cases where the patient just maybe they received an overdose and they didn't wake up at all. Okay, the other disadvantage of ethyl ether as an anesthetic is that it is extremely flammable. Okay, it's both volatile. Okay, the vapors can travel several feet, and it is extremely flammable. As I mentioned last time, methylterbutyl ether was once used as a gasoline additive. It has a very good octane rating, but it was difficult to separate from groundwater in the water treatment process. Okay, I think this is where we left off. Okay, these cyclic ethers do have IUPAC names. Commercially, their common names are more widely used. Ethylene oxide is also known as oxirane. The four-membered ring is known as oxetane. Tetrahydrofuran, or THF, also has an IUPAC name, but almost no one uses that name. The common name is THF. That's what it's known as commercially and also in the chemical literature. Okay, the last compound is 1,4-dioxane. Okay, this one has two ether groups. We start numbering at one of the oxygens, so that's where we get the 1,4. These last two are widely used as solvents. Ethylene oxide is an important intermediate in the manufacture of a number of other organic chemicals. Okay, even though the name includes ethylene, you can see there's no double bond. Okay, this comes from the idea that this started out as ethylene, and then we formed this oxide that bridged both of the carbons. Okay, that's like ethylene glycol. Ethylene glycol does not have a double bond, but it's made from ethylene. All right, ethers are polar molecules. Each CO bond is polar covalent. However, only weak attractive forces exist between ether molecules in the pure liquid. Okay, so ether molecules do not hydrogen bond with each other. Okay, so there's some London dispersion and some dipole-dipole forces. Okay, if we compare ethanol and dimethyl ether, Okay, they have exactly the same molecular weight, molecular formula. You can see they have very different boiling points. Ethanol can hydrogen bond. Dimethyl ether can't. Ethanol has infinite solubility in water, whereas dimethyl ether is 7.8% soluble. Okay, since its boiling point is minus 24, it would therefore be a gas at room temperature. All right, 1-butanol and diethyl ether have the same molecular formula and the same molecular weight, but again, they have very different boiling points. They actually have similar solubilities in water. Ethyl ether boils at 35 degrees Celsius, which is about 95 Fahrenheit. Okay, so if you have a very warm laboratory, the ethyl ether can actually start to boil. All right, and then here's some other examples. Butane diol, okay, if we compare that with 1-butanol, which is only partially soluble, if we have 2 alcohol groups on a 4-carbon chain, then that is now infinitely soluble. Okay, you can see that that also significantly raises the boiling point. Butyl methyl ether has a similar molecular weight, but it has a considerably lower boiling point and much less solubility in water compared to 1,4-butane diol. Ethylene glycol dimethyl ether, okay, boils at 84. Okay, it turns out that this is infinitely soluble. Okay, let me draw the structure of that. Okay, this is ethylene glycol dimethyl ether. This is sometimes called DME, dimethoxyethane. The IUPAC would be ethane. Here we keep the E. And it would be 1,2-dimethoxy. Okay, this is also a very useful solvent. Okay, it's infinitely soluble in water because it has 2 oxygens that water can form hydrogen bonds with. Right, so here's an important point, and that is that ethers are hydrogen bond acceptors only. They are not hydrogen bond donors. You have 2 lone pairs on the oxygen, which could accept a hydrogen bond, for example, from water or from an alcohol or a carboxylic acid. But they cannot hydrogen bond with each other. Okay, I discussed this earlier, so I'm going to go ahead and go on. Right, what about reactions of ethers? Okay, unlike alcohols and alkenes that we've talked about earlier, which have several different reactions, ethers don't actually have that many. Okay, they resemble hydrocarbons, alkanes specifically, in their resistance to chemical reactions. They do not react with strong oxidizing agents such as chromic acid. Okay, we saw earlier in the chapter that chromic acid can convert primary alcohols to aldehydes or carboxylic acids, secondary alcohols to ketones. Ethers are also not affected by most acids and bases at moderate temperatures. Okay, because of their good solvent properties and general inertness to chemical reactions, ethers are excellent solvents in which to carry out organic reactions. Okay, as I mentioned just a few minutes ago, they are extremely flammable. Okay, so they can react with oxygen in the presence of a heat or a spark. Okay, three-membered ring that contains the ether group, the cyclic ether, is called an epoxide. And commonly, this one is ethylene oxide, this is propylene oxide. Ethylene oxide is synthesized from ethylene and oxygen. Okay, this is primarily the industrial process, using silver as a catalyst. Okay, more commonly in the laboratory, we would use a peroxy acid to synthesize an epoxide. Okay, earlier in the semester when we were talking about functional groups, one of the ones we listed was a carboxylic acid, and acetic acid would have the formula CH370 double bond OH. Okay, that's acetic acid. Okay, notice here that there's an extra oxygen in peroxyacetic acid. Right, ethers are generally unreactive to aqueous acids. Epoxides, however, react readily because of the angle strain in the three-membered ring. Okay, so there's energy released when that ring opens up. The reaction of an epoxide with aqueous acid gives a glycol, or a 1,2-diol. Okay, notice that the alcohol groups are trans to each other. Okay, so let's take a look at the mechanism. The mechanism of acid-catalyzed hydrolysis, hydrolysis means splitting using water, of an epoxide involves 3 steps. Okay, the first one is to add a proton. The second step is to react an electrophile and a nucleophile to form a new covalent bond. And then the third step is we take away a proton. Okay, so hydronium ion is present at the beginning, it's present at the end, and so it is a catalyst. Right, so the first step is the oxygen of the epoxide picks up a proton. Water acts as a nucleophile. It attacks one side or the other. And this is symmetric, so it doesn't matter which side. Okay, and when it does that, it forms a bond, and then this bond between the carbon and the oxygen breaks. The electron pair moves toward the positively charged oxygen. All right, and then in the last step, water removes an extra hydrogen, which regenerates the hydronium. Okay, the 2 alcohol groups are trans to each other because water has to attack from behind. And when it attacks from behind, it pushes this hydrogen forward. And so this bond is now back. Okay, nothing happened to this bond, so this CO bond is still forward. Okay, so this is stereochemical stereoselective. Okay, let's look at other epoxide ring openings. The value of epoxides lies in the number of nucleophiles that will bring about ring opening and the combinations of functional groups that can be synthesized from them. Okay, for example, if we use ammonia as our nucleophile, we can produce a beta amino alcohol. We can form a glycol, like propylene glycol here from propylene oxide. We could also form a beta mercaptoethanol. Okay, SH as a substituent is a mercapto group, and we'll talk about that shortly. Epoxides are useful building blocks. Okay, here we have the structural formulas of two common drugs, each synthesized in part with ethylene oxide as a building block. Okay, this is procaine or novocaine, and then this is diphenhydramine or Benadryl. And the region here that's highlighted shows that this is where the epoxide group was located. All right, now we'll move on to thiols. The functional group of a thiol is an SH or sulfhydryl group bonded to an sp3 hybridized carbon. Okay, sulfur is right below oxygen in the periodic table. And so like oxygen, it normally forms two bonds. And the carbon-sulfur hydrogen bond angle is bent. Sulfur is not nearly as electronegative as oxygen. And so if we look at the electron paramagnetic map, we don't see nearly as great a charge separation as we would with an alcohol. Okay, let's move back. Okay, right, so here is methanol. You can see there's a much greater charge separation. Okay, so let's look at naming thiols. The parent chain, again, is the longest chain that contains the thiol group if the thiol is the dominant functional group. Okay, the suffix for thiol, of course, is thiol. For common names, these aren't used so much in the literature anymore. They are used somewhat in the oil and gas industry. The older name for thiols was mercaptan, which is a form of mercury capture. These groups will bind very tightly with mercury and other heavy metals. Okay, if the SH group is a substituent, then it's a mercapto. Okay, so this first one is, we call this one ethane thiol. Okay, we retain the E, the next letter is a consonant, ethane thiol. Commonly, this is called ethyl mercaptan. Okay, this one is 2-methyl 1-propane thiol, or isobutyl mercaptan. And then here, the alcohol takes priority, and so the SH is a mercapto group, so 2-mercaptoethanol. Right, ethane thiol is it's a gas at room temperature. It has a strong rotten egg odor, and it is deliberately added to natural gas so that one can detect a gas leak by its odor. Okay, so when you smell a gas leak, this is actually what you're smelling. The human nose is very sensitive to this. We can detect extremely small quantities of ethane thiol. In the gas industry, it's called ethyl mercaptan. Right, 2-mercaptoethanol. Okay, this is a reagent that some of you who are doing research in cell biology may have used this compound. Okay, I alluded to the odor of ethane thiol. Many low molecular weight thiols will have a stench. Okay, 2-butene-1-thiol has this structure. This one is 3-methyl-1-butane-thiol. Okay, this is a natural product. This is one of the major components of the skunk scent, 2-butene-1-thiol. It's an oily liquid. It is not especially soluble in water. Okay, the sulfhydryl group or the thiol group doesn't hydrogen bond. And we saw earlier with that electron paramagnetic map, there was not a lot of polarity. Okay, this is one of the compounds that's present in the skunk scent. Okay, this is another one. And then these are some natural gas odorants in addition to the ethyl mercaptan that I showed you earlier. Okay, so these have a rotten egg odor. Most of you are familiar with the skunk scent. Okay, the difference in electronegativity between sulfur and hydrogen is pretty small. Okay, so that bond has low polarity. And because of the low polarity, thiols show little association to each other through hydrogen bonding. They have lower boiling points and are less soluble in water than alcohols of comparable molecular weight. Okay, so methane thiol is a gas at room temperature. 6 degrees Celsius is its boiling point. Okay, compared to methanol, which can hydrogen bond, and this has a boiling point of 65. Okay, here's a comparison of ethanol and ethane thiol. You can see, again, because of hydrogen bonding, the ethanol has a higher boiling point. Okay, this is a key difference between thiols and alcohols, and that is acidity. Thiols are stronger acids than alcohols. Ethanol has a pKa of 15.9. Ethane thiol has a pKa of 8.5. And for comparison, acetic acid is 4.74. Okay, so each one of these units, again, is a power of 10. Okay, so that's 7 powers of 10, or about 10 million times more acidic than ethanol. Okay, whereas ethanol won't react appreciably with something like hydroxide, ethane thiol will. Okay, so this reacts with sodium hydroxide to form this thioate salt and water. And because water is a weaker acid than the thiol, this reaction goes to completion. Okay, so that's a key difference. Thiols are more acidic than alcohols. Okay, there's also some differences when it comes to oxidation. Thiols are oxidized by a variety of oxidizing agents, including oxygen, to disulfides. Disulfides, in turn, are easily reduced to thiols by several reagents. Okay, so here we have 2-mercaptoethanol, and using a mild oxidizing agent, we can form this disulfide. Then this disulfide can then be reduced back to the thiol. Disulfides are stable compounds. Okay, if we compare that to the oxygen analog, okay, this is a peroxide. Okay, in contrast, peroxides are very unstable. The bond between the two oxygen atoms is very weak. Peroxides are explosive. It just takes heat or light or even mechanical shock to detonate peroxides. Okay, so this is another big difference between sulfur and oxygen. Okay, I'm going to talk about this last point in just a moment. This interconversion between thiols and disulfides is an important reaction in protein chemistry. Okay, here we have lipoic acid. It's a growth factor for many bacteria and protozoa, and it is an essential component of several enzymes involved in human metabolism. Okay, the functional groups that are present in lipoic acid, we have a carboxylic acid, and then we have a disulfide. During human metabolism, the disulfide bond is reduced to two thiol groups. Okay, so what would happen here? Okay, is the ring would open. Okay, some other comments about thiols. Okay, in protein structure, three-dimensional structure here. Okay, this represents some globular protein, and one of the ways that these proteins maintain their three-dimensional shape is through disulfide bonds. There are some other ways, such as salt bridges and hydrogen bonds and so on, but this is an important component of protein structure. the keratin protein in hair contains a lot of disulfide bonds. Okay, when someone gets a permanent wave, what happens is that a reducing agent is applied to break the disulfide bonds, a process called softening. And one of the compounds that's used to reduce the disulfide bonds is this one called thioglycolic acid. All right, so this breaks the disulfide bonds, or it breaks some of the disulfide bonds. Okay, you can control the number of disulfide bonds by the concentration and the time. Okay, and then after the disulfide bonds are broken, the hair is set on rollers or it's straightened. And then what's called a fixing solution is applied. This is usually something like dilute hydrogen peroxide. And what this does is it reforms disulfide bonds, but the disulfide bonds are not in their original locations. So this imparts a permanent wave to the hair. All right, the other thing that I want to mention has to do with the skunk scent. Okay, if a dog or a person is sprayed by a skunk, okay, what is the remedy? Okay, traditionally, it's been said to use tomato juice. What this actually does is it only covers up the odor. It doesn't really take care of the problem. But what the best way of dealing with skunk spray is to use a mixture of hydrogen peroxide, baking soda, which is sodium bicarbonate, and mild detergent. The hydrogen peroxide will facilitate the formation of disulfide bonds. Sodium bicarbonate, okay, will deprotonate some of the thiol groups, and something like 2-butene-1-thiol is not very soluble in water, but once we make the conjugate base and we form an ionic group, okay, that's going to be more soluble in water, so this will be more easily washed off. And the disulfide is likely to be fairly hydrophobic, but with the presence of mild detergent, you can wash it away. Okay, so this is the remedy for skunk scent. Thiols typically have strong odors, and we talked about the presence of thiols, for example, as natural gas odorants, as components of the skunk scent. Also foods that have strong odors like garlic and onions contain thiols and also some other sulfur compounds. The thiol compounds are not always unpleasant as far as their odors. Maybe a matter of opinion. This is one in particular that I find the odor pleasant. Okay, this is a compound that's given off when coffee is freshly brewed. So this is one of the main odor components of freshly brewed coffee. Okay, I'm going to go ahead and end there. Test next Friday will cover through the end of this chapter. Okay, we will not have live Zoom next week. I will have a couple of one or two recorded review sessions. We'll have some practice exercises, and then the test will be online on Friday. Okay, so we will not have live Zoom at all next week.